Somewhere out there in the vastness of space, invisible monsters lurk. They don't glow, they don't reflect light, they don't make a sound, but they can swallow entire stars, distort time, and warp reality itself. Today we're diving headfirst into the most extreme objects in the universe, black holes. A black hole is a region in space where gravity is so intense that nothing, not light, not radiation, not even information, can escape. Think about that for a second. These are cosmic vacuum cleaners with an appetite for everything. So how do they form? When a massive star, we're talking at least 20 to 30 times the mass of our sun, runs out of nuclear fuel, it loses the ability to fight back against gravity. The core collapses under its own weight. In the most violent cases, this ends in a spectacular explosion called a supernova. But sometimes, the collapse is so extreme, the star gets crushed into an infinitely dense point. That point is what we call a singularity, and that's the heart of a black hole. Now imagine taking Earth, shrinking it down to the size of a marble, but keeping all its mass intact. That's the kind of compression we're talking about here, only way more extreme. Around the singularity lies the event horizon, the boundary where escape becomes impossible. It's not a solid surface like a planet or a wall. It's more like an invisible point of no return. Cross it and you're gone, forever. From the outside, black holes are invisible. You can't see them directly, but we know they exist because of what they do to the space around them. When a black hole feeds, pulling in gas, dust, and sometimes even entire stars, the material spirals in, forming a glowing high-energy accretion disk. That's where things start to get weird. As matter falls in, it gets hot, extremely hot. We're talking millions of degrees. It emits X-rays that we can detect with space telescopes, and the gravity is so strong it actually bends light around it. That's gravitational lensing, a phenomenon where light from stars behind the black hole gets distorted and magnified. In fact, some black holes help us see things we otherwise never could. And then, in 2019, we got the first actual image. Remember that blurry orange donut? That was the shadow of a supermassive black hole in the center of galaxy M87, 55 million light-years away. Captured by the Event Horizon Telescope, this image proved black holes aren't just theoretical. They're real. They're out there, and they're enormous. Speaking of size, not all black holes are the same. Some are just a few times the mass of our sun. These are called stellar mass black holes. Then you've got intermediate mass black holes, the cosmic middleweights. But the true titans are supermassive black holes, millions or even billions of times more massive than the sun. We think they sit at the centers of most galaxies, including ours. In fact, there's a supermassive black hole right at the center of the Milky Way, about 26,000 light-years away, called Sagittarius A, and it's 4 million times the mass of the sun. Now let's get into the weird stuff. What happens if you fall into a black hole? Let's say you're feeling adventurous. You put on your best spacesuit and aim your ship toward a stellar mass black hole. At first everything seems fine, but as you get closer things start to stretch, literally. The gravity on your feet is stronger than on your head. The result? Spaghettification. Yes, that's the actual scientific term. You'd be stretched out into a long, thin noodle. It sounds ridiculous, but it's absolutely real. From your perspective, you'd fall in pretty quickly, but for someone watching from far away, you'd appear to slow down, frozen at the edge of the event horizon, your light red shifting and fading until you vanish. That's time dilation in action, predicted by Einstein's theory of general relativity. Time moves slower the closer you get to a massive object. Near a black hole, it practically stops. So what's at the center? What actually happens at the singularity? We don't know. That's where physics breaks down. General relativity says one thing, quantum mechanics says another, and right now, the two don't agree. We need a theory of quantum gravity, a unified way to explain how the very large and the very small behave in extreme conditions. Until then, the singularity remains a mystery, a kind of cosmic question mark. But here's where things get even more mind-bending. Some scientists think black holes might not destroy everything they take in. Instead, they could store that information or even send it somewhere else. Could black holes be wormholes, bridges to distant parts of the universe, or even to other universes? That's speculative, but not impossible. At the very edge of theoretical physics, black holes are gateways to possibilities we're only beginning to imagine. There's also the information paradox. According to quantum theory, information can't be destroyed, but black holes seem to erase everything. This contradiction has baffled physicists for decades. Then came Stephen Hawking, who proposed that black holes actually emit tiny amounts of radiation, what we now call Hawking radiation. Over trillions of years, black holes might slowly evaporate, disappearing completely. But what happens to the information inside? Does it escape? Is it encoded in the radiation? No one knows for sure. But experiments in quantum physics, string theory, and holographic principles suggest we may be closer to the answer than ever before. And get this, the entire universe might be behaving like a hologram. That is, everything we experience in 3 dimensions could actually be encoded on a 2-dimensional surface, much like information on a black hole's event horizon. It's called the holographic principle, and it's one of the strangest and most profound ideas to come from black hole research. So here we are. We started with invisible monsters. We ended up questioning the nature of space, time, and reality itself. Black holes aren't just exotic objects out in deep space. They are clues. Clues to a deeper understanding of how the universe works, how it began, and maybe even how it ends. One day, we may understand them completely, or one day they might help us understand everything. Until then, they remain cosmic riddles wrapped in gravity, beautiful, terrifying, and endlessly fascinating. If you made it this far, thank you for exploring the universe with us. Be sure to like, subscribe, and drop a comment below. What's the next great space mystery you want us to unravel?